Hi everyone. So here we are going to discuss the concepts of module 4, and here we are going to discuss the three chapters, chapter number 9, 10 and 11. Chapter number 9 deals with virtual memory, chapter number 10 deals with file system concepts, and chapter number 11 deals with file system implementation concepts. So we'll go on discussing one by one chapter here. We already discussed the memory management concepts, and here we are going to discuss the concepts called as virtual memory, where we are going to discuss virtual memory. So what is the need of virtual memory? When there is a memory is insufficient, the memory is inefficient or insufficient, we are using the concept called as virtual memory. Or there is another requirement of the virtual memory: when you are loading the program that is larger than the available physical memory, then we are using the concept called as virtual memory. So here we are going to cover these topics under the virtual memory background. That we are going to discuss the definition of the virtual memory and the benefits, and then we'll discuss the implementation of the virtual memory, that is demand paging, and we'll discuss the how the virtual memory is going to benefit or increase the creation of the processes, and we'll discuss the page replacement algorithms, allocation of frames, and thrashing. These are the topics we are going to cover one by one here. First of all, we'll see the definition of the virtual memory. So it is a separation of user logical memory from the physical memory. Only part of the program needs to be in a memory for the execution using the virtual memory concept. So logical address space can therefore be a much larger than the physical address spaces here, and allows the address space to be shared by the several processes, and allows for more efficient process creation. So these are the benefits of the virtual memory, and some more benefits are there. We are going to discuss later how the virtual memory concept is going to help or increase the or reduce the IO operations and increase the number of users. And the virtual memory can be implemented via the two different methods or the ways. One is demand paging, another one is demand segmentation. So here we are going to cover the demand paging concepts. Before going to discuss the implementation of how the virtual memory is implemented, we'll see the view of the virtual memory, how the virtual memory is larger than the physical memory. So you see the diagram here, there are four things are there. One is swap or the back store area, and another one is physical memory, and there is a virtual memory. And all this virtual memory is the bigger than the physical memory, and there is a need of mapping the pages from virtual memory to the physical memory. That is going to be done by the memory mapping concepts. So this is our view of the virtual memory, or how virtual memory is larger than the physical memory. So this is a virtual address space, how actually the program or the code is loaded here. So as you see how the process are represented in the memory, same way we are going to manage the virtual address space for all the programs, that is code data heap above the top stack, and in between the stack and heap there is a hole that is going to be called as free area, and this is used to grow the stack and heap here. So this is one example or the benefit of the virtual memory. Virtual memory is going to helpful for the shared memory or shared concepts here. So there are two processes executing, and if they are required the same libraries, instead of maintaining separately, those are maintained in the pages, and those pages are going to be shared by both the processes. So instead of maintaining separately, we have maintained at the center, and these pages are going to be used by both the processes. This is going to be another advantage which saves the frames or the pages or the space of the main memory. So now we are going to discuss how actually we are going to implement the virtual memories. This is the first method we are going to use for the implementation of the virtual memory, called as demand paging. So what actually demand paging means, it is going to bring a page into a memory only when it is needed. So if that page is demand, then only that is going to be loaded from the secondary storage to the main memory. So it is going to be provide the different benefits using this virtual memory concept implemented using demand paging. So there's first benefit is less input output operation is needed here, and only the needed pages we are loading into the memory demand pages, so it required the less memory space. and the faster response, because small amount of code is or part of the program is loaded into the memory, that is going to be executed and we are going to get the responses faster. And if there is a less memory needed, automatically the more number of users or more programs are going to be loaded into the memory, that is going to achieve the multitasking and multi-programming objectives, that is effective utilization of the CPU and the memory. And what is actually demand paging here? When there is a page is needed, a reference to it, if that page is not needed, we need not to reference it, and whichever the page is needed by the instruction or the code or the program, and that is invalid reference not in the memory, then we are going to partially abort the program and you raise the message not in the memory and ask the operating system to bring to the memory. This is how we are going to pages are loaded into the memory whenever they are needed. So transfer of the pages from memory to contiguous disk space. So there are two programs, program A and program B, and program A has completed or not no more required, that is swapped out and stored into the backing store area, and the program number B is required, that is loaded into the 17, 18, 19, is swapped into a main memory. So this is called as swapping out and swapping in the needed pages into the main memory. This is how actually we are going to transferring the pages from memory to contiguous and contiguous disk space and disk space to memory. So here how we know that page is demanded or demanded page is referenced or invalid reference. So for that we are using the one bit, that bit is called as valid and invalid, and that is going to be added into the page table. So with each page table entry we are going to add a valid and invalid bit is going to be associated. So here we are going to use 1. If bit is set to 1, the page is in the memory. If the bit is set to 0, that page is not in the memory. Initially valid and invalid bit is set to 0 for on all entries. Example of the page table snapshot is shown in the below figure. So here some of the bits are set to 1, means these pages are in the memory or these pages are reference, and the bits are set to 0 or invalid reference or not in the main memory or physical memory. So during the address translation, if a valid invalid bit in the page table entry is 0, means that page is not in the memory, then operating system will raise the trap called as page fault. Page fault means the page that is requested by the uh, or demanded by the program is not in the memory, that is called as page fault. So this is one example, that is a page table. So when going to show some pages are not in the main memory. Example here, logical memory, there are 6, 7, 8 pages A, B, C, D, E, F, G, H, and this is a page table and it is a physical memory, and these are the pages in the backstore, that is A, B, C, D, E, F. So among these we are going to have only 3 pages are loaded into the physical frames of the physical memory, that is A, C, F. So those bits are going to be only set to 0, that is page number 0, frame number 0, address space 0 is going to contain A, fourth frame containing the data A or A page, sixth frame containing the C page, and ninth frame containing the F page. And the other pages are not loaded in the physical memory, they are in the logical memory. Those are set to an invalid bit. And when the process demands the another page, consider that example, which pages are there ACF, and it is F page requested another page linked with a library, and that is going to be contained by the page H. So it will verify the page table and it will check for the valid invalid. Now it is a bit is set to invalid, that is 0 or I. Now it will raise a error called as page fault. Now the question is, what is page fault and how to handle it? If there is a ever if there is ever a reference to a page, first reference will trap to operating system. Means what here, if there is a invalid reference to the page or the page is not in the memory, then the operating system will raise an error called as page fault. So when there is a page fault, operating system looks at another table to decide invalid reference bit. If the invalid reference bit abort and just not in the memory, it is going to tell it just not in the memory. After that, operating system will start searching the empty frame in the physical memory, swap the page into a free frame, and reset the table validation bit is equal to 1 or V, and restart the instruction execution. That is the least recently used, that is called as block move, and auto increment and decrement location. This is how the page fault is going to be handled. And the next, it is going to show the diagram how actually the page fault is handled. So when you are going to load the page M or instruction M, page M, it will search for the page table first. It will check is that page is a reference or invalid reference based on the bit reference. The bit reference is set to I, means what? The page is not in the memory. Then it will trap. Operating system will trap to the it will trap to the operating system saying that the page fault or the page is not in the memory. When that trap is raised to the operating system will start searching, or it will locate the page in the backing storage area. This is a backing storage area in the third step. And then OS will search a pre-frame in the physical memory, and in that pre-frame the page will be bring in the missing page. Once that page is bring or loaded into the memory, you are going to reset the page table with a valid bit. Once you set the valid bit, it will start the restart the instruction execution by the CPU. So these are the different steps we are using to handle the page fault.